Good day, esteemed researchers and viewers tuning in from around the world. We're excited to present our research titled Latent Fingerprint Matching via Dense Minutia Descriptor. I'm Ziyu Pan, joined by my colleagues Yangjia Duan, Shangjun Guan, Jianzhang Feng, and Jia Zhou. Our work introduces a novel approach to fingerprint matching. Addressing the challenges of low genuine match overlap areas, we've developed a three-dimensional construct, the dense minutia descriptor, that significantly enhances matching performance. Stay tuned as we delve into the intriguing insights and implications of our research. Moving on to the key highlights of our study, our primary motivation was to enhance fingerprint matching performance. To achieve this, we introduced a novel concept called the dense minutia descriptor, or DMD. This innovative approach addresses the persistent issue of low genuine match overlap areas in latent fingerprint matching, a problem that has been a significant hurdle in the field. Now, let's talk about the problem we addressed. Existing methods have been struggling with these low genuine match overlap areas. Moreover, we observed that current approaches might not be fully exploiting the potential of integrating different features for improved performance. Our DMD aims to fill this gap, offering a more comprehensive and effective solution for fingerprint matching. In essence, our work is a step forward in overcoming the challenges in latent fingerprint matching, and we believe it opens up new avenues for further research and development in this area. Moving on to the key highlights of our study, we've introduced a dual-branch architecture for training our model. This architecture integrates two distinct features, the texture feature and the minutia feature. This combination greatly enhances the model's performance. We've also emphasized the importance of a normalization strategy that takes into account the overlapping region. This strategy significantly improves the matching performance of our model, especially in scenarios of low genuine match overlap areas in latent fingerprint matching. Our key contribution is the introduction of DMD, a three-dimensional construct for fingerprint matching. This construct encapsulates robust abstract features, enhancing the representational capacity of DMD. Our evaluations show that DMD outperforms competing methodologies in terms of rank 1 identification rate and true acceptance rate metrics. In summary, our study presents a novel approach to fingerprint matching, offering improved performance and efficiency. Thank you. Begin a frame. Frame title. Key highlights. Begin itemize. Item main idea. Method. Begin itemize. Item. Our DMD utilizes a strategic selection of training samples and a dual-branch architecture for training. This dual-branch design integrates different features, enhancing the model's performance. Item. We experimented with various modifications, such as omitting the normalization approach, decreasing DMD dimensionality, and merging two branches into one. These steps allowed us to understand the impact of each component on the overall performance. Item. Notably, the normalization strategy significantly improved the DMD matching performance, addressing the common scenario of low genuine match overlap areas in latent fingerprint matching. Item. Even with reduced dimensionality, the DMD outperforms a single branch model of the same dimensionality. End itemize, end frame. On this slide, we delve into the key highlights of our research. Our dense minutia descriptor, or DMD, demonstrates impressive resilience, maintaining robust matching performance even after a binarization process. This is a significant finding, as it suggests potential for secure template encryption. In our ablation study, we observed that while performance does decrease as dimensionality reduces, the DMD still outperforms a single branch model of the same dimensionality. This underscores the robustness of the DMD and its ability to maintain good performance even after modifications. In essence, our research highlights the robustness of the DMD and its potential for secure template encryption. It's a testament to the power of integrating different features, such as texture and minutia, into a dual-branch design. This is a promising step forward in the field of fingerprint matching, and we're excited to see where it leads us next. Begin a frame. Frame title. Our approach. Dense minutia descriptor, DMD. Begin a mini page. T. A 0.5 line width. Begin itemize. Item. Our solution. Dense minutia descriptor, DMD. Begin itemize. Item a three-dimensional construct aligning with the original image plane and encapsulating robust abstract features. Item utilizes strategic selection of training samples and a dual-branch architecture for enhanced representational capacity. Item outperforms other methods in rank 1 identification rate and true acceptance rate, TAR, metrics, even after undergoing a straightforward binarization process. End itemize, end a mini page, hfill, begin a mini page. T a 0.5 line width, begin a figure, centering, include graphics, height equals 0.8 text height, a src task underscore execution, extracted underscore paper underscore data, 2405.01199v1 figures, 2405.01199v1 figure 2:1.png. Caption app performance comparison of DMD with other methods on NIST SD27 and end-to-end latent datasets. End of figure, end a mini page, end a frame, backquote. On this slide, we're comparing the traditional one-dimensional minutia descriptor with our proposed dense minutia descriptor, or DMD. As you can see in the figure, DMD is a three-dimensional representation that takes into account the overlapping area for score normalization. This is a significant improvement over existing methods, which often struggle with low genuine match overlap areas in latent fingerprint matching. Furthermore, these traditional methods may not fully harness the potential of integrating different features. Our DMD, on the other hand, effectively addresses these issues, leading to enhanced fingerprint matching performance. Begin a frame title a DMD performance and ablation study, begin a mini page, T as 0.5 line width, begin a figure, centering, include graphics, height equals 0.8 text height, a src task underscore execution extracted underscore paper underscore data, 2405.01199v1 figures, 2405.01199v1 figure 2:1.png, end a figure, end a mini page, hfill, begin a mini page. T is 0.5 line width, begin itemize, item figure. Performance comparison of DMD with other methods and the impact of various modifications on DMD. Item DMD outperforms other methods in rank 1 identification rate and true acceptance rate, TAR. Item, even after binarization, DMD maintains good matching performance. Item ablation study. Normalization strategy improves DMD's performance. Reducing dimensionality decreases performance, but DMD still outperforms a single branch design. End itemize, end a mini page, end a frame. Backquote, begin a frame. Frame title a DMD architecture and performance. Begin mini page. T is 0.5 line width. Begin itemize. Item DMD architecture. Begin itemize. Item DMD is built on a modified RESNET34 backbone. Item it features a dual branch structure, one for texture descriptor and the other for minutia descriptor. Item A 2D positional embedding is used to enhance spatial information processing. End itemize. Item DMD performance. Begin itemize. Item DMD outperforms other methods in rank 1 identification rate and true acceptance rate. Item it maintains good performance even after binarization, improving matching efficiency. End itemize, end a mini page, hfill, begin a mini page, T as 0.5 line width, begin a figure, centering, include graphics, height equals 0.8 text height, a src task underscore execution, extracted underscore paper underscore data, 2405.01199v1 figures, 2405.01199v1 figure 2:1.png, caption a DMD's dual branch architecture and performance comparison with other methods, end a figure, end a mini page, end a frame, backquote, begin a frame title a deep dive into DMD and its architecture, begin a mini page, T is 0.5 line width, begin a figure, centering, include graphics, height equals 0.8 text height, a src task underscore execution extracted underscore paper underscore data, 2405.01199v1 figures, 2405.01199v1 figure 2:1.png, end a figure, end a mini page, hfill, begin a mini page, T as 0.5 line width, begin itemize, item figure. the architecture of our dense Minutia Descriptor (DMD) network, showing the dual branch structure and the final DMD. Item DMD architecture, begin itemize. Item the backbone is a modified RESNET34, with a dual branch structure for texture and Minutia descriptors. Item each branch uses a 2D positional embedding to incorporate spatial information. Item the final DMD is a combination of the two descriptors, timed by the segmentation map. End itemize. Item descriptor extraction, begin itemize. Item the texture branch outputs a segmentation map and a texture descriptor. Item the Minutia branch generates a Minutia descriptor and a Minutia map. Item the final descriptor is a combination of the texture and Minutia descriptors, timed by the segmentation map. End itemize, end mini page, end frame, begin a frame title a deep network and descriptor extraction, begin a mini page, T as 0.5 line width, begin a figure, centering, include graphics, height equals 0.8 text height, SRC task underscore execution, extracted underscore paper underscore data, 2405.01199v1, figures, 2405.01199v1 figure 2:1.png, end a figure, end a mini page, hfill, begin a mini page, T as 0.5 line width, begin itemize, item figure. The architecture of our dense Minutia Descriptor (DMD) network. It utilizes a dual branch structure to extract texture and Minutia features. Item, the DMD network is based on a modified RESNET34 architecture, preserving the details of fingerprint ridges. Item, the dual branch structure focuses on texture and Minutia features, each complemented by a segmentation map and a Minutia map respectively. Item, the final DMD is a combination of these descriptors, providing a robust and efficient solution for fingerprint matching. End itemize, end a mini page, end a frame, begin a frame title a deep network and descriptor extraction. Begin mini page, T is 0.5 line width, begin itemize, item figure. The architecture of our dense Minutia Descriptor (DMD) extraction network. It's a dual branch structure. One branch for texture descriptor and the other for Minutia descriptor. Item, the DMD is a three-dimensional construct, with 2 dimensions aligned with the original image plane and the third encapsulating robust abstract features. Item, the network incorporates a 2D positional embedding to enhance spatial information during descriptor comparison. End itemize, end a mini page, hfill, begin a mini page, T as 0.5 line width, begin a figure, centering, include graphics, height equals 0.8 text height, SRC task underscore execution, extracted underscore paper underscore data, 2405.01199v1 figures, 2405.01199v1 figure 2:2.png, end a figure, end a mini page, end a frame, In this slide, we delve into the existing fingerprint matching methods and their limitations. A common challenge in the field is the low genuine match overlap areas in latent fingerprint matching. This is due to the inherent poor quality of latent fingerprints, often found at crime scenes, which are blurred and subject to background noise interference. Moreover, there's a limitation in the underutilization of the potential of integrating different features for improved performance. Current methods either focus on fixed-length descriptors or minutia-based representations. While fixed-length descriptors enhance indexing efficiency, they struggle with the nuanced description of latent fingerprints. On the other hand, minutia-based techniques provide superior accuracy but are less efficient. In essence, the field is in need of a method that can effectively handle the challenges posed by low-quality fingerprints and efficiently integrate different features for improved performance. In the following slides, we will introduce our proposed solution to address these issues. In our exploration of existing methodologies, we've seen a variety of approaches to fingerprint matching. Each has its own strengths and weaknesses, and there are areas where they all could improve. This brings us to our proposed solution. The Dense Minutia Descriptor, or DMD. Unlike traditional methods, DMD is a three-dimensional construct, aligning 2 dimensions with the original image plane and using the third to encapsulate robust abstract features. This unique structure, combined with a dual-branch architecture, allows DMD to refine and enhance its representational capacity. This innovative approach sets DMD apart from existing methods and represents a significant step forward in the field of fingerprint matching. begin a frame, frame title a DMD's superiority and interpretability, begin itemize, item DMD's three-dimensional construct. Two dimensions align with the original image plane, and the third encapsulates robust abstract features. Item DMD's performance remains superior even when compared to its binary variant. Item Figure 5. Comparison of three types of descriptors, MCC, MinNet, and DMD. DMD's feature pattern closely resembles its best match, indicating its robustness against noise and inaccuracies. Item Figure 6. DMD's top NM patch matching accuracy surpasses others, demonstrating its potential in large-scale fingerprint indexing. End itemize, end frame, begin a frame, frame title modifications and performance, begin itemize, item exploration of DMD modifications, begin itemize, item decreasing DMD dimensionality from C equals 6 to C equals 3 and merging two branches into a single one, item despite performance deterioration, DMD with reduced dimensionality still outperforms the single branch one, item dual branch design integrating texture and minutia features, enhances model's performance, end itemize, item performance of DMD against other methods, begin itemize. Item DMD outperforms other methods in rank 1 identification rate and true acceptance rate metrics. Item DMD maintains good performance even after binarization, improving matching efficiency and potential for secure template encryption. End itemize, end a frame, begin a frame. Frame title a conclusion and future works. Begin itemize. Item introduction of a deep network-based dense minutia descriptor, DMD, that outperforms other methods in terms of rank 1 identification rate and true acceptance rate, TAR, metrics. Item despite its effectiveness, DMD's performance is dependent on the accuracy of minutia extraction processes. There's potential for improvement by using a more robust latent fingerprint minutia extractor. Item current approach does not use enhanced fingerprints as input. Future work includes developing a latent fingerprint enhancement method to improve DMD's performance. Item in scenarios where minutia extraction is inadequate, the use of virtual minutia as anchor points could enhance DMD's matching performance, especially for small fingerprints from mobile devices. End itemize, end a frame, On this slide, we delve deeper into the technical details of our proposed dense minutia descriptor, or DMD. As you can see in the figure, the DMD extraction network is characterized by a dual-branch architecture. This structure is designed to integrate two distinct features, the texture feature and the minutia feature. The DMD is a deep network-based descriptor, specifically developed for fingerprint matching. It's important to note that our evaluations have shown that the DMD significantly outperforms other methods in two key metrics: the rank 1 identification rate and the true acceptance rate, or TAR. In essence, our DMD methodology offers a robust and efficient solution for fingerprint matching, setting a new standard in the field. We'll be discussing more about its unique features and performance in the following slides. Moving on to the technical details of our research, let's delve into the structure of the dense minutia descriptor, or DMD, extraction network. As you can see in the figure, the DMD is a three-dimensional construct. The first two dimensions align with the original image plane, capturing the spatial layout of the fingerprint. The third dimension, however, is where the magic happens. It encapsulates robust abstract features, providing a rich representation of the fingerprint. This unique design allows the DMD to capture and represent intricate details, making it a powerful tool for fingerprint matching. Stay tuned as we explore more about the dual-branch architecture and the integration of texture and minutia features in the upcoming slides. Moving forward, let's delve into the technical details of our proposed research. As you can see in the figure, we have a detailed structure of the DMD extraction network. This network is unique due to its dual-branch architecture. This architecture integrates two key features, the texture feature and the minutia feature. The integration of these features significantly enhances the model's performance. In addition to this, we have strategically selected our training samples. This strategic selection has been instrumental in refining and enhancing the representational capacity of DMD. In essence, Our approach combines a unique architecture with a thoughtful selection of training samples to create a robust and efficient model. This model not only performs well, but also provides a deeper understanding of fingerprint matching. Moving on to the technical details of our research, let's delve into the structure of the DMD extraction network, as depicted in the figure. This network is characterized by a dual-branch architecture, integrating both texture and minutia features. One key aspect of our approach is the normalization strategy. This strategy is designed to take into account the overlapping region between fingerprints. By doing so, it significantly enhances the performance of DMD matching. In essence, our method is not just about creating a new descriptor, but also about how we process and normalize the data. This approach allows us to effectively address common challenges in fingerprint matching, leading to improved results. Remember, the goal here is to enhance the accuracy and efficiency of fingerprint identification, and our DMD extraction network is a significant step towards achieving that goal. Moving forward, let's delve into the technical details of our proposed research. As you can see in the figure, our dense minutia descriptor, or DMD, extraction network is characterized by a dual-branch architecture. This structure integrates both texture and minutia features, enhancing the model's performance. We've made several modifications to the DMD, such as omitting the normalization approach, reducing the DMD dimensionality, and merging the two branches into one. Despite these changes, it's important to note that the DMD still outperforms single-branch models of the same dimensionality. This highlights the robustness and adaptability of our model, even when subjected to significant alterations. In the next slides, we will further explore the impact of these modifications on the performance of the DMD. Stay tuned. Begin a frame. Frame title: a deep dive into DMD. Begin a figure. Centering: include graphics. Width equals 0.8 text width. Height equals 0.45 text height. A SRC task underscore execution extracted underscore paper underscore data 2405.01199v1 figures 2405.01199v1 figure 2:1.png. Captiona Tinea, the DMD extraction network, highlighting the dual branch architecture. End a figure. Begin itemize. Item DMD is a three-dimensional construct, with two dimensions aligned with the original image plane, and the third encapsulating robust abstract features. Item: the dual branch architecture is key to DMD's performance. One branch focuses on texture features, the other on minutia features. Item: the DMD maintains good performance even after undergoing a straightforward binarization process, contributing to improved matching efficiency. Item: ablation studies show that normalization and maintaining dimensionality are crucial for optimal performance. End itemize. End a frame. Moving on to the technical details of our research, let's delve into the structure of the dense minutia descriptor, or DMD, extraction network. As you can see in the figure, the network is designed with a dual-branch architecture. This structure allows us to integrate two distinct features, the texture feature and the minutia feature. Now, let's talk about the performance of DMD. Our evaluations show that DMD significantly outperforms competing methodologies. We use two key performance metrics for these evaluations: the rank 1 identification rate and the true acceptance rate, or TAR. In essence, our DMD extraction network, with its dual-branch architecture and integration of texture and minutia features, provides a robust and efficient solution for fingerprint matching. It's a significant step forward in the field, and we're excited to see its potential applications. In this slide, we delve deeper into the technical aspects of our research. Firstly, we highlight the potential for secure template encryption. This is made possible due to the robust performance of our dense minutia descriptor, or DMD, even after a binarization process. This not only improves matching efficiency, but also opens up avenues for enhanced security measures in fingerprint matching. Secondly, we shed light on the feature visualization of DMD. This is a crucial aspect as it provides interpretability within the context of fingerprint matching. By visualizing the features, we can better understand how DMD works and how it contributes to improved fingerprint matching performance. This understanding is key to further refining and enhancing the descriptor. In essence, our research presents a promising approach to fingerprint matching, with potential applications in secure template encryption and a clear understanding of the underlying features at play. Let's now turn our attention to the technical results of our study. As you can see in the figure on the left, we've compared the performance of our dense Minutia Descriptor, or DMD, with other methods on the NIST SD27 and N2N latent datasets. The key takeaway here is that DMD, which is a deep network-based descriptor, significantly outperforms other methods in fingerprint matching. This superiority is reflected in two crucial evaluation metrics: the rank 1 identification rate and the true acceptance rate, or TAR. What's more, DMD maintains its high performance even after a binarization process. This robustness not only speaks to the strength of DMD but also opens up possibilities for secure template encryption. So, in essence, our DMD is not just effective, but also versatile and secure. In conclusion, we've introduced a novel approach to fingerprint matching with the dense Minutia Descriptor, or DMD. This is a deep network-based descriptor that provides a three-dimensional construct, capturing robust abstract features. This construct aligns two dimensions with the original image plane, while the third dimension encapsulates these abstract features. The training of DMD is a strategic process. We've selected our training samples carefully and employed a dual-branch architecture. This architecture integrates texture and minutia features, enhancing the representational capacity of DMD. One branch focuses on texture, producing a texture descriptor and a segmentation map. The other branch is dedicated to minutia, generating a minutia descriptor and a minutia map. In essence, DMD is a powerful tool for fingerprint matching, outperforming other methods in terms of identification rate and true acceptance rate metrics. It's a testament to the potential of deep learning in the field of biometrics. Thank you. In conclusion, our normalization strategy takes into account the overlapping region, which effectively addresses the challenge of low genuine match overlap areas in latent fingerprint matching. This is a significant step forward in the field of fingerprint identification. In terms of performance evaluation, we've benchmarked our method against others using the NIST SD27 and N2N latent datasets. The results are promising. Our approach outperforms others in terms of rank 1 identification rate and true acceptance rate metrics. This means our method is not only more accurate, but also more reliable in accepting genuine matches. These findings open up new possibilities for the future of fingerprint identification, and we look forward to further refining our approach and exploring its potential applications. Thank you for your attention. In our study, we found that the dense Minutia Descriptor, or DMD, maintains a strong performance even after a binarization process. This is a significant finding as it not only contributes to improved matching efficiency, but also opens up the potential for secure template encryption. Moving on to our ablation study, we observe that while the performance of DMD does deteriorate as dimensionality reduces, it still outperforms a single branch model of the same dimensionality. This suggests that our dual branch design, which integrates different features, greatly enhances the model's performance. In conclusion, our findings underscore the robustness and versatility of DMD in the field of fingerprint recognition. We believe that these insights will pave the way for further advancements in this area.